Hi, welcome back. Today we're going to talk about positive semi-definite matrices, which was a concept that we defined at the very end of last lecture. So here, all I've done is just copied and pasted from lecture 12 slides the definition of a positive semi-definite matrix. Okay, so by definition right now, we're only defining this for symmetric matrices, and we say that it's positive semi-definite if you take the associated quadratic form. Remember we said for every symmetric matrix, you can associate a quadratic form where you take x transpose ax. That's a homogeneous degree 2 polynomial, and you can graph it, and you can see, does it always lie above the domain, or is it always greater than or equal to the domain? And we said that if the graph is always greater than or equal to the domain, it's always non-negative, then you call it positive semi-definite. And if it's actually always positive except at the origin where it equals 0, then you say it's positive definite. Okay, and what we ended on last time actually was we defined these things called principal minors of a matrix. Remember, these are certain determinants of certain submatrices where you delete the same rows and the same columns, and then you take the determinants. And then we saw how many principal minors there were. So for an n by n matrix, there were 2 to the n minus 1 principal minors, one for each subset of the columns, other than you can't take all of the columns, right? And then we also saw the leading principal minors, and those are the principal minors where you only deleted all the stuff at the end, right? And there are, of course, n of those, because you could delete nothing, you can delete just the last row, you can delete just the last 2 rows, just the last 3, ... You can delete all but one of them, right? So that gives you n possible leading principal minors. And today what we're going to see is that this is related to a way to understand positive semi-definite and positive definite matrices. Okay, so let's go back to this. This is the definition we had before. Now we're going to make a theorem that gives us a bunch of different conditions that are equivalent to being positive semi-definite, and one for positive definite as well. Okay, and here is the positive semi-definite one first. So this is a definition / theorem. Okay, so a symmetric matrix, again, these definitions only make sense for symmetric matrices, not for just general matrices, is called positive semi-definite. And I'm going to introduce some new notation for this. And it's going to be kind of a weird greater than or equal to sign. Okay, the point is that matrices aren't numbers, so you can't say that A is greater than 0. That doesn't make any sense. Greater than is only defined for real numbers, really, right? So I'm going to use this to sort of mean like A is greater than or equal to 0, but by that I mean that it will be positive semi-definite. Okay, if any of the following equivalent conditions are true. Okay, so the first one is the thing that I called the definition last time. So x transpose ax is greater than or equal to 0 for all x in Rn. In other words, the graph of QA of x's quadratic form is on or above the domain. Right, like those pictures that we saw last time. So one way, I mean, this was the way that I defined positive semi-definite matrices last time. Your quadratic form is always above the domain. Okay, here's another equivalent characterization. It turns out that for a symmetric matrix, this is the same thing as saying that all the eigenvalues of A are non-negative. Okay, we'll see why some of these conditions are equivalent later. 3, there exists some matrix B such that A is equal to B transpose B. To me, this one is kind of the most surprising that it's the same. right? So I can imagine that, oh, the eigenvalues of A tell you something about what the graph of the quadratic form will look like. All the eigenvalues being non-negative seems pretty reasonable that it translates to, oh, the quadratic form is always non-negative. I could believe that. But that you can write A as B transpose B if and only if all of the eigenvalues are non-negative isn't very intuitively obvious to me. We will see why, but I think like this is kind of a surprising fact. It's surprising that this is equivalent. If you asked me to guess before I knew any linear algebra, I would never have guessed this equivalent condition. Okay, and then the fourth is all principal minors of A are non-negative. Okay? So this is why we talked about principal minors a second ago. Technically, I guess in order to check the first condition, you'd have to check every possible matrix or every possible vector x and Rn in principle. You'd have to graph a whole function. That seems kind of hard. For 2, you'd have to take a characteristic polynomial, find its roots, and make sure they were all non-negative. So you'd have to check n of the roots. Have to factor a degree n polynomial. That one actually seems more doable than the first one, I would say. But I don't know, if I gave you a degree 6 polynomial and I asked you if all the roots were non-negative, I'm not sure you'd be so happy that I asked you that question. Okay, 3 is, it seems like this would be impossible to check. Again, we'll see why it's true, which will tell us how to build a matrix B. But if I gave you a matrix A and I said, can you write this as B transpose B? I don't think you would be able to do it right now. But this is actually a checkable condition. You'd have to check 7, for a 3x3 matrix, you'd have to check 7 determinants. You'd have to check 2 to the n minus 1 determinants. But determinants you can do, right? So I think this one to me seems the most checkable. At least if n is small. Maybe 2 is also like fairly checkable if n is small. 3 is the most miraculous. That's my opinion of this definition / theorem. And again, we'll see why some parts of this are true. Okay, that's positive semi-definite. Now you should ask, okay, well, what about positive definite? What do I need to change here, right? It should be a stronger definition. In part 1, for example, it should be greater than 0. And you might guess that part 2 is that all eigenvalues are positive. That's true, actually. I don't know if you'd have any guesses about 3 and 4, though. Okay, so here's the definition / theorem. So a symmetric matrix, again, these definitions only work for symmetric matrices. A in Rn by n is called positive definite. And we'll use the notation a funny looking greater than sign to mean positive definite if any of the following equivalent conditions hold. Equivalent conditions hold. So 1 is the definition that we saw last time. X transpose AX is greater than 0 for every vector X in Rn. Every non-zero vector X in Rn. Right, of course, if you plug in X, you'll get 0. In other words, the graph intersects the domain at the origin, but is always above other than at the origin. Okay, 2 is, I said you were correct if you guessed it, all eigenvalues of A are positive. That again seems very believable to me. 3 is the one with the B transpose business. So there exists some matrix B such that A is equal to B transpose B, and B has linearly independent columns. Right, so this should be a stronger condition because being positive definite is stronger than being positive semi-definite. So positive semi-definite means you can write it as B transpose B. Being positive definite means and for that matrix, the columns are linearly independent. Okay, notice that B will not, in general, be a square matrix. I'm not saying that it's a square matrix. So I wouldn't say for some invertible matrix B. If B were square, then linearly independent columns would be the same thing as being invertible. Just that you can write it as B transpose B for some matrix that has linearly independent columns. And then 4, which was the thing about the principal minor, the principal minors, you might guess that it should be something like all the principal minors of A are positive, but that's actually not the condition. The condition is just that all of the leading principal minors of A are positive. It's actually a bit better. So leading principal minors of A are actually positive. Okay, of course, all of the principal minors will be non-negative. That's because it's also positive semi-definite, so all the principal minors are non-negative, but you just need to check if the leading ones are all positive or not. So some of the other ones can be 0. The leading ones, though, have to be positive. Okay, and then there's a note in the notes, which I think is a good point, which is if you can write A is equal to B times B transpose B, then if you let C be the matrix B transpose, then A is the same thing as C transpose. So you might see the definition given as there exists some matrix A, B, such that you can write it as A equals B times B transpose. But that's exactly the same as this thing, because if you can write it as B transpose B, then you can write it as C transpose, where C is the transpose of B. So you might see that definition maybe somewhere else. That's exactly the same condition, though. Okay, now another thing to remember is we've already seen matrices that look like B transpose B before. We've studied things that look like this when we were studying orthogonal projections. We saw things like this. When studying orthogonal projections. And if you remember, we saw that, so that matrix that I circled is a square matrix. B could be a rectangle, but B transpose B is square. And we saw that if the columns of B are linearly independent, then B transpose B will be invertible. Right? Go back and watch, or go back in your notes and see. We actually did see that. So in the positive definite case, because the matrix B will have linearly independent columns, that B transpose B will be invertible, which means that the matrix A will be invertible. Okay, but actually that was easier to see than that fact, because one of the leading principal minors of A is the determinant of A itself. Right, so the fourth condition tells us that the determinant of A has to be positive, which means that A will definitely be invertible. Right, so now somehow the equivalence of 3 and 4 seems like maybe a little bit more believable. At least there's some evidence that it's kind of consistent. If 3 is going to be true, then A will have to be invertible. If if 4 is going to be true, then A will have to be invertible. So all positive definite matrices are invertible. I guess another thing is from part 2, all the eigenvalues are positive, and we proved in a homework that the product of the eigenvalues is the determinant of A. So that's also consistent with the fact that all positive definite matrices will have to be invertible. Okay, so let me just make that as a comment. So from 2, 3, and 4, we can see that, I almost said it is clear that, but sometimes it's not that clear, but we can still see it. We can see that positive definite matrices are invertible. Okay, and of course, if some of the eigenvalues are 0, then it could still be positive semi-definite. So positive semi-definite matrices may or may not be invertible, right? But I guess what's true is that the positive definite matrices are exactly the same thing as the invertible positive semi-definite matrices, right? Because positive semi-definite means all of your eigenvalues are non-negative. The only way to be positive definite is for them to all be positive, which would make the matrix invertible. And if it is invertible, then none of the eigenvalues can be 0 anyway. So if it's positive semi-definite and invertible, then it's going to be positive definite, right? So note that by the definition part 2, positive definite is the same thing as positive semi-definite plus invertible. Okay, but before we do the next thing, which is we're trying to prove that these conditions are equivalent to one another. That will be our next goal. Before we do that, let's look at some examples of positive semi-definite matrices and sort of verify for ourselves that they satisfy all the properties, just to make sure that this definition theorem isn't complete garbage. So I guess I could have done this on this slide. Here's an example. The matrix A equals 1, 2, 2, 4 is positive semi-definite. Okay, why? Because it satisfies any of the 4 equivalent conditions. Let's actually check them. Right, so the first one has to do with a quadratic form associated to this symmetric matrix. So what is a quadratic form? It's you multiply by xy on the left, the row vector, the column vector on the right, and what you get is you get this xy row vector times x plus 2y, 2x plus 4y. And so you'll get x squared plus 2xy plus 2xy plus 4y squared, which is x squared plus 4xy plus 4y squared, which is x plus 2y squared. Okay, and since it's x plus 2y squared, no matter what you plug in for x and y, you'll always get a non-negative number. Right, this thing is greater than or equal to 0 for every xy. And it can, in fact, sometimes equal 0, right? Like if x is 1 and y is negative 1/2, then you'll get that to be 0, even not at the origin, right? So this is only positive semi-definite. Another way that you could have seen that is the columns of A are clearly not linearly independent, so this is not going to be invertible, so it's definitely not going to be positive definite. Okay, so it's going to be positive semi-definite, because that quadratic form is always non-negative. The eigenvalues we can just compute. It's an easy exercise, or plug them into Julia. The eigenvalues are 0 and 5, so all the eigenvalues are non-negative, which should have been true since it's positive semi-definite. Now, the magic is, where do we get this B from? So if I let you know that B is the matrix 1, 2, then B transpose is the matrix 1, 2, then B transpose B is 1, 2 times 1, 2, and that gives you exactly the matrix 1, 2, 2, 4, which is A. So for this example, it's maybe kind of actually easy to see what B would have to be. But that's still fine. Notice that the columns of B are not linearly independent because the columns here are just 1 and 2 single set of R1. So one of them is a scalar multiple of the other, so these are not linearly independent. Okay, so remember a second ago I said, oh, well, you could state it instead as CC transpose. If you state it like that, then what you need is the C transpose has linearly independent columns. So you would need to be a little bit careful. It isn't exactly this with the transpose shifted. You also need to shift the transpose here as well. Okay, that's the third condition. And what's the fourth condition? The fourth condition has to do with the principal minors. And there are only 2 principal minors, right? There's the determinant of the matrix itself. The determinant of A is 0 because it's not invertible. And then the other principal minors, sorry, there's 3 principal minors. It's 2 squared minus 1. The other principal minors are when you delete the first row in the first column, and when you delete the second row in the second column. And so the minors are determinant of 1, which is 1, and determinant of 4, which is 4. And so all of the principal minors of this matrix are non-negative, including one of them being 0. Okay. Another thing to note here is that this factorization that I wrote down for A as B transpose B is not going to be unique. It's not unique. You could take -1, -2 to be your other B, and that will satisfy the same property, right? So this is only unique up to a minus sign when B has 1 row. Okay, so let's look at a slightly bigger example that will also be a positive definite example rather than just positive semi-definite. Let's let A be the following matrix. 2's along the diagonal, 1's everywhere else. This thing we'll see is positive definite. Okay, so 1, the first condition, has to do with the quadratic form, right? So what's the quadratic form? The quadratic form is going to be in 3 variables, and what you do is you multiply by x, y, z on the left of the matrix and x, y, z on the right of the matrix. And what you'll get 2x squared plus 2y squared plus 2z squared plus 2xy plus 2xz plus 2yz. And this is the same thing as x plus y plus z squared, which is in fact always positive for all non-zero x, y, z in R3. This isn't right. It is what's written in the notes, but this isn't right. This actually is not always non-zero, because if you plug in like x equals 1, y equals 1, z equals -2, that's because this factorization is wrong, right? We're off by an x squared plus y squared plus z squared term. So let me fix that. This is equal to x squared plus y squared plus z squared plus x plus y plus z squared, which is greater than 0 for all x, y, z in R3. This is easy enough to see because each of these terms is always greater than or equal to 0. This term is always greater than or equal to 0. But if you want to make the thing equal to 0, then they all need to be 0, which means that x and y and z all need to be 0. Right? So the only way to make that quadratic polynomial 0 is to let x, y, z be 0. In other words, it's positive for every non-zero x, y, z. Okay, so slight typo in the notes there. It's not really that big a deal. Okay, 3, you can, by 3 I mean 2, of course. 2, you can compute the eigenvalues of A, again, by hand if you want, or using Julia, and the eigenvalues are 1, 1, and 4, which are all positive. That is true. 3, which is how I suspect the easiest way to write an example of a positive definite matrix, is to take, let our B be this matrix. You just choose some matrix with linearly independent columns. You can check that this matrix has full rank. And then B transpose is, of course, just the transpose of this matrix. 0, 1, 1. 1, 0, 1. You can just check that B transpose B is equal to A. So you can, in fact, write it as B transpose B, where B and B transpose both have full rank here, rank 3. B has 3 linearly independent columns. And 4, we just need to check the leading principal minors of A. So first we need to take its whole determinant, right? Its determinant, I suppose, is 4, because we already know its eigenvalues. So that one is positive. Then I need to delete just the last row in the last column. And so the determinant of that one, really it's the thing that we called D sub 3, to use the notation from before. That's determinant of this matrix, 2, 1, 1, 2. And so that's 3. And then D2, 3, that's the last principal minor. That's the determinant of just 2, which is 2. So as you can see, all of these leading principal minors are all positive. So, at least for these two examples, it was true A positive semi-definite meant the quadratic form was, I mean, that's the definition. The quadratic form was always non-negative, but we saw that the eigenvalues were non-negative. You could write it as B transpose B, where the columns of B weren't necessarily linearly independent, and all of the minors of A, in this case there are only 3 of them, but all of the minors of A were non-negative. Same thing for the positive definite. We saw that in this example, this matrix satisfied all 3 of the properties. All 4 of the properties that we said were equivalent to being positive definite. Okay, I guess I should have said that here, note that this B is not unique. So this B is not unique because if I choose any Q with orthonormal columns, so choose Q is a K by K matrix. Sorry, R K by K. Right. In general, this B is going to be a N by K matrix. Do I mean N by K? I do mean N. No, I mean K by N. Sorry. In general, B is going to be a K by N matrix. A is going to be N by N, of course, right? B transpose is N by K. If you choose Q and R K by K, that's orthonormal. Then you can let then you can take the matrix QB instead of B. So you take QB, transpose QB, and you'll get B transpose Q times B. And we said for an orthonormal matrix, its transpose is its inverse. So this is B transpose B. And there are infinitely many orthonormal matrices, right? Because there's infinitely many bases of RK, and so you just put them as the columns of a matrix after you normalize them. Sorry, infinitely many orthogonal bases. You can just rotate the coordinate axes however you want. And so you will have infinitely many choices for B, but this was one choice for B. Okay, and I said this is probably how you come up with actually positive semi-definite or positive definite matrices. You can just come up with the B, take its transpose, and B transpose B will be guaranteed to be positive semi-definite. That's one of the equivalent definitions. So let me just state that as an example, as it's stated in your notes. So if you choose any B, any matrix you want, and let A equals B transpose B, then A will be positive semi-definite. Okay, note that we proved in a homework that if B has rank K, let me state it like this: if the rank of B is K, then that's also the rank of B transpose. And we saw in a homework that if you multiply 2 matrices together, the rank of the product is at most the rank of the lesser of the 2. Right? In particular, we saw that. So the rank of A, which is the rank of the product of these 2 rank K matrices, is less than or equal to K. So if you want A to be invertible, you're going to need to take K to be N. I guess at least N? At least N. So for A to be invertible, we need K to be at least N. In particular, if you want a rank 1 positive semi-definite matrix, which will be an important subclass of positive semi-definite matrices, then you could just take your B to be a 1 by n matrix. In other words, a row vector, and B transpose will then be a column vector, right? So in particular, the rank 1 n by n positive semi-definite matrices are of the form V transpose for V in Rn. Okay, now it's actually not that obvious yet, right? Because maybe I take a 2 by n matrix that has rank. I mean, it's possible for the rank of a rank 2 times a rank 2 to be 1, right? I just said less than or equal to. I didn't say it was actually equal to k. But it turns out they will always be able to write the rank 1 ones as a vector times the transpose of a vector, right? So in this notation, I should say, like, this vector transpose is B, right? This is an n by 1, sorry, a 1 by n matrix. In other words, it's a row vector, and this one is the B transpose. Okay, now what we want to do is we want to see that these conditions are equivalent to one another. So again, I think it's not obvious from looking at them. And I guess the proof that we'll do is just the first 3 are equivalent to each other. I guess the principal minors thing is beyond the scope of this class. So let's prove it. So I guess we should restate it. Let me just state it briefly. A symmetric A and Rn by n is positive semi-definite if and only if any of, so 1 is Q, let's be really brief, X transpose AX is greater than or equal to 0 for all X and Rn. That's the quadratic form one. 2, all eigenvalues are non-negative. That's the eigenvalue characterization. And 3, there exists a matrix B in R k by n such that A equals B transpose B. And that's the one that's sort of hardest to believe. Okay, so first, let's show that if, first let's show 1 if and only if 2. Okay, so let's call this 1 if and only if 2. That will show that 1 and 2 are equivalent, and then we just need to prove that 3 is equivalent to either one of them. Okay, so suppose that 1 holds. So in other words, suppose that X transpose AX is always non-negative for every vector X and Rn. Okay, now I want to show that all the eigenvalues are non-negative. Let's actually take an eigenvector and an eigenvalue, right? And let's let U be an eigenvector. So A times U is equal to lambda times U for some scalar lambda. I want to show that that scalar lambda is a non-negative scalar, right? But I want to use this property that I know about any vector transpose times A times that vector is greater than or equal to 0. So we should do that with U. We should do that with this eigenvector, right? Then if I look at U transpose AU, notice that this thing is U transpose times lambda times U, which is the same thing as lambda times U transpose U. But U transpose U is the length of U squared, right? But we just said I get to assume that U transpose AU is positive, so this thing, or non-negative, so this thing is non-negative. Okay, but the point is that U, the length of U, is always a positive number because U is an eigenvector. It was non-zero, right? Since U not equal to 0. Eigenvectors are non-zero, so that length, this length is positive, and therefore lambda is greater than or equal to 0, because lambda times a positive number is non-negative, right? So that shows that if the quadratic form is always non-negative, you just apply the quadratic form on an eigenvector, and you get that the eigenvalue has to be non-negative. Okay, so now let's see the other way. So now suppose that lambda 1 through lambda n, the eigenvalues of A are all non-negative. Okay, now we're going to use the full power of what we saw last time, or a couple lectures ago, which is if you're a symmetric matrix, then you can get an orthonormal set of eigenvectors. Right? So since A is symmetric, we only made this definition for symmetric matrices. There is an orthonormal set of eigenvectors. U1 through UN. Right? It's diagonalizable by because it has n orthonormal eigenvectors. That was one of the things we learned about symmetric matrices. Okay, so now, the U1 through UN form an orthonormal basis of Rn. Okay, and we know for sure that for any I, if I look at UI transpose A UI, I'll get UI transpose lambda I UI. So I'll get lambda I UI transpose UI. That's for each of the UIs, right? But this is lambda I times the length of UI squared, but the length of UI is just 1, right? So this is equal to lambda I, which we assumed was positive, or non-negative rather. Okay, so if all the eigenvalues are non-negative, then if I do this U transpose AU with an orthonormal set of eigenvectors, then I'll definitely get that the U transpose AU for those eigenvectors will be non-negative. I need to show that actually it's true for every vector in Rn. But I have a basis of Rn, which means that I should be able to do something with that. Right? So now let x be any vector in Rn. I need to understand x transpose Ax. But since the UIs form a basis, I can just write x as C1U1 up through CNUN. Now I'll take x transpose Ax, and since the UIs are an orthonormal basis, all of the cross terms will be 0 because you take the dot product of an orthonormal basis with itself, you get only zeros and ones, right? So then x transpose Ax is the sum of CIUI transpose times A times the sum of CIUI. So I've just, again, written x in terms of the basis. Now, when I multiply this A times UI, I'll get lambda I UI. So if I take let's just expand this product here. So this is still CI UI transpose, the sum. This one here will be the sum of lambda I CI UI. Because when you multiply by A, in each summand, you just pull out the correct eigenvalue. Right? But now I have a bunch of, like the sum of a bunch of orthonormal basis vectors dotted with the sum of a bunch of orthonormal basis vectors. So a bunch of the terms will die, and a bunch of the terms, the CIs are, the UI dotted with itself is going to be 1. Right, so this is one, I can break it up into 2 sums. One sum where I'm dotting the same I with the same I. Right, so in that case, I'll get CI squared UI transpose UI times lambda I. And then I'll get all the terms where they're different. All I not equal to j, CI CJ, lambda I lambda j, UI transpose UJ. Right? All the terms in this product are either the i's match or the i's don't match. But all of these quantities are 0. And all of these quantities are 1, because this is an orthonormal basis. And so what you'll get here is you get just the sum from I equals 1 to n of ci squared lambda I. But remember, I assumed that all of my lambda i's were non-negative, and ci squared is going to be non-negative, so this is greater than or equal to 0, and this is greater than or equal to 0 for every I, and so this whole thing is greater than or equal to 0. And so I just showed if you take any x in Rn, then x transpose ax is greater than or equal to 0, which shows that 1 and 2 are equivalent. Okay, so we sort of said at the beginning, or when we looked at this definition, that it's kind of believable that non-negativity of the quadratic form would say something about non-negativity of eigenvalues. And the point is that if you're a symmetric matrix, then you can get an orthonormal set of eigenvectors. And so the eigenvectors and the eigenvalues tell you basically everything you need to know about all of Rn in terms of A. That's the rough idea. Because it's symmetric, knowing that the eigenvalues are non-negative basically tells you that it always does something non-negative. All right. Now, I want to show that if 3 is true, then 1 is true. So the next step in my proof is 3 implies 1. Okay, so suppose that there exists K by n matrix B such that A is equal to B transpose B. Let's suppose that you can write A as B transpose B. I want to show that the quadratic form is always going to be positive. Non-negative, sorry. All right, so we want to show x transpose AX is greater than or equal to 0 for all x in Rn. Okay, but this is actually maybe the simplest part of this proof, because we just do what we have to do, right? So let x be in Rn. Then x transpose AX, let's just write x as B transpose B, which we can do. And now hopefully you can recognize that this is the same thing as this. This is looking better and better. This is bx transpose times bx, which is the same thing as the length of bx squared. And again, lengths are always non-negative, so this is greater than or equal to 0. So because you can write it as B transpose B, if you take x transpose B transpose bx, you're going to get the length of bx, which is always non-negative. So this shows that if you have 3, then the quadratic form is always non-negative. Okay, so now lastly, let's show 1 implies 3. So suppose that A is a symmetric matrix, which we supposed at the beginning, and this quadratic form is always non-negative for all x in Rn. Okay, so this is, again, where we're going to need to use the fact that A is symmetric so we know quite a bit about it. Since A is symmetric, we know that it admits an orthonormal diagonalization. We know that it's diagonalizable and that you can actually choose an orthonormal basis of eigenvectors. Right, so since A is symmetric, it admits an orthonormal diagonalization. So let's write that as A is equal to Q lambda Q transpose, because Q is the letter we generally use for orthonormal matrices, and the inverse of an orthonormal matrix is its transpose. Okay, now, since x transpose AX is greater than or equal to 0, that's what I'm assuming here, then by the exact same thing that we saw on this page, we know that all of the eigenvalues of A are non-negative. We already showed that, right? So I'm trying to show that 1 implies 3, but certainly we know that if you assume 1, then all the eigenvalues are non-negative. So by the first part of this proof, all eigenvalues of A are non-negative. So lambda looks like this, and all of these lambda i's are greater than or equal to 0. Which means since they're non-negative, I can take their square root and get some real number, right? So let's define, this is a new symbol. This, in general, symbol doesn't make any sense for matrices. I'm just defining it for this specific matrix, and I'm going to take the square root of each of the diagonal entries, and this is now still an Rn by n because each of the lambda i's was non-negative. Okay, and the trick is to just let b be the square root of lambda times q transpose. So because all the eigenvalues are non-negative, I can take the square root of each of them, which means I can take the square root of the diagonal matrix appearing in the diagonalization. Now if I let B be this matrix, then what is B transpose B? This is equal to square root of lambda q transpose times, or all transposed times square root of lambda q. Right? But this is just q transpose transpose times root lambda transpose times root lambda, sorry, there's a q transpose missing here, root lambda q transpose. But now, this is a diagonal matrix, so it's equal to its transpose. So this is q root lambda q transpose. But root lambda times root lambda is just lambda, so you get q lambda q transpose. This is just a. So I found a matrix where A was equal to B transpose B, and the whole trick here was, since A is symmetric, it has an orthonormal diagonalization. Since the quadratic form is always non-negative, the eigenvalues are always non-negative, which means that I can actually take the square root of the diagonal matrix, which I can't always do, right? If any of the eigenvalues were negative, then I can't find, or at least it's not obvious to find, a diagonal matrix that squares. I mean, sorry, it's not just not easy to find. You can't find a matrix that squares to the matrix if any of the entries along the diagonal were actually negative. Okay, so hopefully this proof contains all the ideas of why these three things, even though it's not obvious that they're the same, are actually the same. They're all equivalent. And we're really using very strongly that A is symmetric. If A weren't symmetric, then we wouldn't know that you could get an orthonormal diagonalization or an orthonormal set of eigenvectors, which is essential in this proof. We only have a couple minutes left here. Let me point out one thing, which is that matrices of the form B transpose B are sometimes called Gram matrices. But what we just proved is that those are exactly the same thing as the positive semi-definite matrices. So if you ever see the word Gram matrix, this is just the same thing as positive semi-definite matrices. Okay, they're sometimes called Gram matrices for historical reasons, or if when you write them down, it's very obvious that they're B transpose B, right? So the last two things I want to talk about are just the two lemmas that are presented at the end of the notes. I'm not going to prove them. You can read the proof in the notes. And it just tells you about the positive definite case. We talked about the columns of B have to be linearly independent. And it turns out that that's actually the condition that separates a positive semi-definite matrix from a positive definite matrix. Okay, so if the columns of a B1 up through Bn of an n by k matrix are linearly independent, so if you actually have linearly independent columns, then B transpose B is positive definite. Okay, so there's a very brief proof, so I'm going to let you read that in the notes. And that's, the converse is part of the definition of being positive definite, right? We said that if you can be written as B transpose B with linearly independent columns, then you are positive definite. In other words, if you're a positive definite matrix, you can write it as B transpose B with linearly independent columns. So the converse here is actually the definition of being positive definite. But there's a proof given in the notes. Okay, so by the definition, or let me just say, if A is positive definite, then A equals B transpose B, where the columns of B are linearly independent. Okay, I'm not stating anything new here. This is actually just the definition of positive definite. The point is that we haven't proved this part of the definition yet. And the proof is written in the notes. Both of these proofs are like 3 sentences each. So I'm going to let you read them rather than take up more lecture time. Because next time we're going to talk about applications of positive semi-definite matrices, which hopefully is something you've been wondering about. Like, what's the point of studying these things? There will be we'll do several applications, and we'll see why next lecture. All right, see you then.